This is a little introduction to the Who's the Daddy DNA lab. Just to kind of walk you through the general process, we need to get DNA from an individual. So, particularly for a paternity test or maybe forensically at a crime scene, you're looking for hair or blood, a cheek swab there to get the saliva. Whatever it is, we need a source of DNA. Once we get that DNA, we can amplify it by getting the DNA to replicate, or we might have to cut it. That is, to cut it into smaller pieces so that we can get a pattern out of those pieces. So in this case, what we're going to do is we're going to add a restriction enzyme that's going to cut the DNA into pieces. Different people are going to have different patterns of cut pieces. What we do then is take that DNA that has now been cut but is still in solution, and we put it into this gel electrophoresis machine. What happens is the DNA starts to move through the gel. Smaller pieces can move farther. Large pieces get hung up and stuck kind of early on. They form a band. Those bands then make a pattern. We can use those patterns to match up to our original DNA. So for example, in forensics, you can see an example here of the banding pattern. So the bands are forming in this gel. And we have the victim's blood, and then we have the suspect. So we're expecting to find the victim's DNA at the crime scene. But then we have these suspects. We want to see which suspect matches up best with the DNA we found at the crime scene. In this case, you can see that it's suspect 2. Paternity is a little bit different because you're getting half your DNA from your mother, half from the father. So in the case of a paternity test, now we're matching up the mother's DNA, the father's DNA, the baby's DNA. So that child's DNA should have half its DNA from the mother. The other half should match the banding pattern found from the father. So it makes it a little bit trickier, but you're going to want to find the banding pattern that matches the mother's pattern and the father's pattern. So in the case of our lab, what we have are long strips of DNA. You'll see it's going from a 5' to the 3' on the top end, from a 3' to the 5' on the bottom end, and it's just this long sequence of nitrogen bases. The first thing we're going to do is take that JAN1 enzyme and we're going to cut it. That is, we're just going to draw a line, just like you see for the JAN1. We're going to draw a line in that DNA. So anytime I see TGG, I draw a line just like it shows. So I'm going to take my pen here and draw a line just like it shows, TGG. I come down, over, and I cut like that. Now when I'm counting for the size, I'm going to count this whole thing, that whole section of DNA. All right, so the longest piece of that DNA. Then I'm going to look for any other TGGs. I find another one right here. I'm going to cut it the exact same way. Now I have a new section of DNA that looks like this. So that's what the enzyme does. Ward 2 is another enzyme. It's going to cut in between an A and a T if there's an ATA pattern. So I look across the top for any ATAs. I find one, and I'm going to cut it just like that, just like it shows on the Ward 2. So I'm going to keep looking for any other The second enzyme is Ward 2, and in this case I'm looking for a TAT across the top. So anywhere I see a TAT, I would draw a line. In this case, I'm not seeing any TAT. So just the one that we had Here, those are our um, the second enzyme is the Ward 2. So I'm looking for any TATs across the top. And I'm not seeing any TATs. So we're not going to have any segments cut there. So now that I have my DNA cut, I need to mark it. So the way you mark it is with a probe called X38. So anytime I see a complement to TGC, that's where I'm going to color it. So the complement to T is A, the complement to G is C, the complement to C is G. So anytime I see an A, C, and G, that's where I'm going to get a mark. So I'm looking for ACG. So that's going to cause that to be marked. ACG will cause that to be marked. Now these are bands that are going to show up on my gel. So where will they show up? And then I have to just count the number of base pairs to see how long it is. That'll tell me where it shows up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this band is going to show up at 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll notice I'm just counting across the top where it's the longest piece of DNA, whatever that long piece of DNA strand is. 1, 2, 3, 4, 5, 6, 7. So I'm going to put a band mark on my gel at 7. So there will be a mark at 7. There'll be a mark at 10. And then right above it, there'll be a mark at 13. And so that's going to be the pattern from this person in my gel. A mark at 7, a mark at 10, and one here at 13. So if you do that, you can match those patterns up. Remember, half are going to come from the mother, half from the father, and that's where you'll see the baby's paternity outcome.